graduating this May and then on to grad school. So a little bit of an overview. The death of hair cells in our cochlea is what leads to death, and our hair cells do not regenerate. So I'm going to talk to you a little bit about our previous attempts to regenerate hair cells, look at my current work, and future directions after this summer. So for those of you who don't know anything about how our ears actually hear, sound waves come into our ear to the cochlea, where they're received by hair cells. You can see, that was wrong, but sorry. By the purple hair cells here, which are supported by all these brown supporting hair cells, which will become important later. So in our world, there's a lot of noise all around us and other stresses that come to our hair cells and accumulate. So as we're young and we get lots of noise and damage, by the time we're older, we can't hear anything, which is a problem because, as I said, our hair cells do not regenerate. Though we know that non-mammalian vertebrates do have regeneration in their hair cells. And from this, we can form two goals that we have in hair cell regeneration. One is to make the supporting, I'll stop doing that. Make the supporting cells under the hair cells change identity and become hair cells, and also to make them re-enter the cell cycle so that one daughter cell can become a new hair cell and one can replace the original supporting cell and we can retain normal anatomy. So the first goal of identity is generally synonymous with the basic helix-loop helix transcription factor atonal 1, which you see right here, which activates POE4F3 and then growth factor independent 1, and eventually you get hair cell differentiation and terminal hair cell markers such as myosin 6, albumin, and calbindin. We know that it's really important because when we knock out atonal 1, we do not get hair cells in the cochlea, and when we ectopically express it in supporting cells of neonates and juveniles, we can make some supporting cells change identity and become hair cells with these markers here. However, in adults, this doesn't work. So something about adult supporting cells, you're not able to get this transdifferentiation with ectopic atonal 1. And to show you some in vivo data of the ectopic expression of atonal 1, using the Cree-Lock system to knock out a stop codon and ectopically express atonal 1 in the supporting cells. You can see here, this is all in the hair cell layer. The pink is a myosin 6 marker, so they're all hair cells, including these funny-looking cells that have the ectopically expressed atonal 1 that have come up from the supporting cell layer and are expressing these hair cell markers. However, only about 6 to 12% of supporting cells that ectopically express atonal 1 will make this change and come to the become outer hair cell-like immature cells, and it doesn't work in adults, as I said earlier. So we know we can change identity of supporting cells in the juveniles and neonates. Let's see what we can do about proliferation of supporting cells. We know that P27, which is a cell cycle inhibitor, is responsible for maintaining quiescence in adult supporting cells. So you would expect if you took away the cell cycle inhibitor, you'd re-enter the cell cycle. And that's in fact what we see. You can see here the supporting cell has EDU, which shows that the cell is entering synthesis and re-entering the S phase in the cell cycle. And down here you see the green cells still have P27, but in this cell that does not have P27, we're getting synthesis. However, these cells that are proliferating and re-entering the cell cycle are maintaining all their supporting cell identity and not transdifferentiating into hair cells, which won't help us here. So, given that we know how to change identity and we know how to start proliferation, what happens when we put the two things together? And that's what they did in my lab before I got here. You can see here, these are hair cells in the green, and this is the ectopically expressed atonal 1 that has gone up in the outer hair cell layer. And this was really cool because, as you can see here, this is an adult model, and before when we ectopically expressed atonal 1 in adults, we couldn't get these immature hair cells to come up to the outer hair level, and now we can. Also interestingly, though we also had the knockdown of P27 in this model, we weren't getting proliferation. We were just getting the transdifferentiation of the supporting cells, which we weren't able to get before. And you can see here that these cells that were ectopically expressing atonal 1 up in the hair cell layer were expressing markers such as POE4F3, myosin 6, albumin, and calbindin. So this was really cool, but we wanted to know why it was happening. to us that P27 was doing something outside of its cell cycle activities that was helping atonal 1 be able to change the identity of the supporting cells in adults, which we hadn't been able to do before. We know atonal 1 is a basic helix loop helix factor, and it is known that these generally need friends or co-transcription factors to activate transcription of their target genes, such as POE4F3. These include GATA3 and TCF3. So we were thinking perhaps this is the link that we see here, that somehow P27, when it's on, can deactivate GATA3. And without GATA3 there, atonal 1 is not able to change the identity in adults. This is our hypothesis. So we started looking at these factors and whether or not they're expressed in juveniles and adults. We found TCF3 was expressed in both, so not very important probably as there's no change. But GATA3 on the other hand, well, it's present at P0 during neonate time in abundance in all the red here. By the time we get to P30, there's absolutely no GATA3 in the supporting cell layers. And if I take away the DAPI nuclear stain, you can see it's completely dark. There is no GATA3. Here you can see there is a little bit of GATA3 in the inner hair cells. So what we know is that when atonal 1 is ectopically expressed, it cannot turn on GATA3, as you can see here and here. There's no GATA3 in our supporting cells. But when we knock out P27, we are getting a major increase in GATA3, and we expect that this is why, when we do this combined knockout of P27 and ectopic expression of atonal 1, we're able to get transdifferentiation of the supporting cells in adults. So, quick recap. When you ectopically express atonal 1 and knock down P27, we're getting transdifferentiation of supporting cells in adults. We know that P27 is aiding atonal 1 in some way other than the cell cycle, and that the difference we see when we knock down P27 in the ectopic atonal 1 cells is that we get increased GATA3 expression, which leads to our hypothesis that P27 is altering GATA3 in some way. And my aim this summer was to try and find out if this was through transcriptional regulation. And how I did this was I went to cell culture. The cochlea is really small, and it doesn't have very many cells in it, which makes it really hard to do fine molecular work and expression analysis in. So it's cell culture with a couple different cell lines. And I knocked down P27 using A2CE here, which is a drug previously known from my lab to stop transcription of P27. And I also used siRNA. I was then able to collect the cells, extract them, and do qPCR to quantify the expression of P27 and GATA3. So the first cell line I used was a mouse embryonic fibroblast cell, which is not an ear cell. And in this cell, I did find that I could significantly decrease the amount of P27. And that when I did this, it correlated to an almost significant decrease of GATA3. So this is kind of interesting. But again, not a hair cell. So we also have this cool model called the HEI-OC1 cells, and they are immortalized hair cells. And again, I was able to significantly knock down P27 and get a large reduction in GATA3, which was really interesting. Again, if you remember, in the in vivo data previously gotten in our lab, when you knock down P27, you got more GATA3. And here in my cell lines, I'm seeing that there is a reduction. Why could this be? Well, one, maybe the model just doesn't quite fit. These are immortalized hair cells, and our goal, what we're seeing in vivo, is in supporting cells. But basic conclusions I can draw is that there does seem to be some sort of transcriptional level regulation between P27 and GATA3, and that it looks like P27 is activating GATA3 in these MEF and OCI1 cells. But drugs are messy, so we needed to do more than just the A2CE, which is why we attempted to do some siRNA knockdowns, which as of yet haven't come around to being significant yet. You can see slight reductions. So what we're doing now is adding higher concentrations of siRNA to the cells, and hopefully that will get us to a significant level of knockdown so we can quantify GATA3 expression and see if what we saw in the knockdown of GATA3 was indeed because of the knockdown of P27, or if it was because of some off-target effect from the drug. So trying to make sense of the knockdown that I found. It was previously published by Pitt et al. 2011. It shows that in a conditional knockout of a complete knockout of P27 versus wild type, they also got a decrease of GATA3 expression by twofold in meth cells, which theirs was significant, which lends itself to think that mine is also probably going to get to significant as I increase my N. However, interestingly enough, P27, there are two different mutations they also tested. And in one of them, there was pretty much no change in GATA3, and in the other one, there was an increase. So they weren't completely significant. So this one corroborates my data that yes, GATA3 can be turned down when you turn down P27, and also that there might be some sort of bivalency to this kind of regulation that P27 is having on GATA3, which was interesting. To go a little bit further, to bring some importance to what I found, we know that both P27 and GATA3 are really important in cancer biology. We know that specifically, say in breast cancer, lower P27 expression can correlate to a worse prognosis. You can get less ability to go through apoptosis and things like that. We also know that higher GATA3 expression correlates to a better prognosis, and that when GATA3 levels are also going down in, say, breast cancer, you get a higher rate of metastasis and a higher grade tumor. So if we put these two together, which my data seems to say, is that when P27 function is lost, not only are those breast cancer cells losing the ability to go through apoptosis, they're also dedifferentiating because they lose GATA3 and becoming more able to metastasize. So the original problem of losing P27 is conflated, as it also knocks down GATA3 and gives you more problems. So this just shows how some research we already know, linking it together with my data. Future directions, we are still trying to get the siRNA to work, so we can make sure that HCCE isn't just being a bad drug and giving me false data. We're also interested in pursuing perhaps CRISPR-Cas to get a permanent knockout of P27. We also perhaps interested in moving to a cancer model to study further what the P27 knockouts are doing to GATA3. Specifically, we could look at the mechanism by doing qPCR. We could immunoprecipitate the P27 and then run qPCR for GATA3 regulatory elements, which could tell us exactly if it's binding or what's going on. So I'd like to say thank you to Suzanne Gronemeyer and James Marmion, and to the entire Zoe Lab for letting me come in, and especially Bradley Walters for being a wonderful mentor. Any questions?
We have time for one question.
I just have a quick question maybe about is this close to, or is this intended to improve hearing in people, and is it close to doing that?
So the immature hair cells, which I showed you from the ectopic expression of A201 in the juveniles and neonates, and also in the knockdown of P27 and ectopic A201, those are immature hair cells. They start forming kind of weird-looking stereocilia bundles, and neurons are actually coming to them, but they're lacking some really important things like oncomodulin and prestin, which are really, really essential to actually hearing. So far, these new immature hair cells aren't able to actually increase your hearing capacity. They do hearing tests on the mice that they do this, and it's not increasing their hearing capacity. But it's better than nothing. It's halfway there. So it's kind of a step. See what's wrong with these immature hair cells and find out what we need to do to also get those other important factors.
Great, thanks.
Yeah.
Get your lab down for a picture. Thank you.
Rob, what is the song about the alphabet? There's a song that sings the alphabet to you. It's like A, B, C, D, E, F, G. How does the alphabet song go? A, B, C, D, E, F, G. Well, I mean, it's a different song.